In this video, we're going to combine two ideas, that is basic probability and combinatorics and counting problems. So we're going to apply the concepts of permutations and combinations to probability calculations. And we're going to use probabilities to analyze games of chance. We're going to look at lotteries, poker, and talk about Kino as well. So first, let's review the ideas of permutations and combinations and the idea of counting. We can break it up into two different things we have to look at. First, are we going to replace the thing that we are selecting? So if we're looking at numbers, can we repeat the numbers? Or do we not replace what we're looking at? If we are replacing, we can just use the fundamental principle of counting. That is, we multiply the number of options for each selection. If we do not replace the objects, then we can either have permutations or combinations, and that depends on if the order is important. So if the order is important, we use permutations. We look at that as NPR, n factorial over n minus r factorial. And if order is not important, we do combinations. That is n choose r and cr, n factorial over n minus r factorial. Note that sometimes this is written as n over r in parentheses without a fraction bar. All right, so let's look at an example. A group of 3 people is selected. What is the probability that at least 2 of them will have the same birthday? So first we need to think about the probability basics. That is, we are looking at an experiment, we have a sample space, we have an event, and we are looking at the probability, that is the size of the sample space and the event. So the experiment here is to ask 3 people their birthdays. The sample space is the set of all possible list of 3 birthdays. And what we're really interested in here is the size of the sample space, because remember what we're going to be doing is finding the probability of some event, which is going to be the size of that event over the size of the sample space. So to find the size of the sample space, we need to think about how many different combinations of birthdays do 3 people have. So here we have with replacement, because we could have the same birthday more than once. In fact, that's what we're going to really be interested in later on. So we're going to think about with replacement. And we can think about there are 3 things that we're going to put together. There are 365 options for the first. We're going to ignore the leap year just to make this a little bit easier. There are 365 for the second and 365 for the third. I guess I should write that on top here. 365 choices for the first birthday, the second birthday, and the third birthday. So the size of the sample space, how many different combinations of 3 birthdays do we have? We're just going to write that as 365 cubed. So that's going to be the denominator of our probability. Now let's let E be the event that at least 2 people share the same birthday. And we're going to note that it is easier actually to find the number of the complement instead of the actual event. So the complement here is the opposite of at least 2 people sharing the same birthday. That means that no one shares the same birthday. And to find the size of that set, we can think about selecting birthdays without replacement. Note here that order is important, and that's because in our sample space, a outcome such as January 1st, August 8th, December 9th, that is different than August 8th, December 9th, January 1st. The same dates are involved, but the order is important because we're talking about different people here. So we're going to be using permutations because we have order being important, and we're going to be talking about birthdays without replacement. That is how we could find all the possible trios of birthdays that are all different. So this is going to be a permutation with n equal to 365 total birthdays. And we're going to be choosing 3 of them to put in order. So this is 365 P3, which is 365 factorial over 3, oh, sorry, not 3, over 365 minus 3 factorial, which we can write as 365 factorial over 362 factorial, which looks terrible, but we can write this as 365 times 364 times 363 times 362 factorial over 362 factorial. Those cancel, and we have a more manageable operation here. So this is the size of the complement. So our probability here, probability of E, is the size of E over the size of S. That's going to be 1 minus the size of the complement over, here is 365 cubed. This is going to be, sorry, not 1. Sorry, the probability of E is 1 minus the probability of the complement, which is 1 minus the size of the complement over the size of the sample space. There we go, that looks better. And that's going to be 1 minus 365 times 364 times 363 over 365 cubed, which is going to be equal to 0.0082. I should say this is about 0.0082. So that's going to be about 0.82%, which is not a whole lot of chance that could happen. On the worksheet, you're going to find a problem that is similar to this. That's going to be a little bit surprising maybe. And that is, what if you asked a group of 30 people this same question? And the chance that 2 people share the same birthday is going to be much more than 0.82%. And I'll let you figure that out with that problem. All right, so in all these problems we're going to do in this video, we're not really doing anything new. We're just bringing in different ideas together. We're going to be talking about which counting technique to use. We're going to be using the ideas of unions and intersection and complements with our probabilities, and then just use some basic probability ideas as well. So now let's look at some games of chance, talk about different lotteries. So here is a 644 lottery. That is, out of a possible 44 numbers, 6 numbers are chosen. And if the player matches all 6 numbers, they win the first prize. If the player matches 5 of the 6 numbers, they win the second prize. So find the probability of winning the first prize. Well, first let's think about what is the size of the sample space. Here we need to have 44 numbers possible, and we're going to be choosing 6 of them. So note that to find this, to count this, we're going to know that we are going to have without replacement. We can't choose the same number twice. And here, order is not important. We don't really care what the order of the numbers is. We just need to match our 6 numbers. So this means that we're going to be using combinations here. So how many different lottery tickets are possible. How many different ways can we choose 6 numbers from 44? Well, note that here we have 44 possible numbers, and we are going to choose 6 of them. That's going to give us 44, choose 6, 44 factorial over 44 minus 6 factorial times 6 factorial, which is going to be 1 over, that's going to be 7,059,052. So here the probability of our event, we should say that our event is that the ticket, or our numbers match the winning ticket. And the size of that event is just 1. There's only one way that's possible, and that is we match all the numbers. So here the probability of this event is the size of the event itself over the size of the sample space. It's going to be 1 over 7,059,052. And it's useful to write this as a fraction. We'll see on the next page why that's the case. The next question says, what's the probability of winning the second prize? The second prize says that we match 5 of 6 numbers. So note that the size of the sample space is the same. There are still that many tickets possible, but now our event, which is we match 5 of 6 numbers, has a different size. Here, we're going to use a combination. We have, of the 6 numbers, we are going to match 5 of them. And this will give us 6 choose 5, which is equal to 6. But what that represents, these are just the winning numbers. We also need to see how many opportunities there are for the one losing number. So if we match 5 of the 6 winning numbers, there's 6 ways that we could do that. Then there's one losing number, and there are 38 possible losing numbers. So we use the fundamental principle of counting. We have 6 winning numbers, or 6 ways to have the winning numbers, times 38 ways to have a losing number. So here, the size of our event is going to be 6 times 38. And we're going to write that as the probability 6 times 38 over our sample space, which is going to be about 0.0003228. So here's our probability, here's our answer, and the bottom of the page talks about how decimals may not be actually the best way to represent this, and that's because it's hard to kind of get a good intuition as to what that number represents. But if we think about it as a fraction, Note that 0.00003228 is about 0.0003. And we can write that as a fraction, thinking about that as 3/100ths. And this is 3 times out of 100 or 100,000, we win the second prize. That kind of gives us more intuition as to what that actually represents. All right, so in this problem, we had to break it up into 2 different parts. How many different ways we could get those 5 winning numbers? There's 6 of them. And then in each of those, we have a choice for whatever losing number we want. And there are 38 possible losing numbers. Let's do another lottery problem. Here we're going to talk about the Powerball lottery. 5 numbers from 1 to 59 are chosen, and then a Powerball number from 1 to 39 is chosen. Find the probability of matching all 6 numbers. So let's start with our sample space. How many different tickets are there? How many different ways can we get 6 numbers here? Well, we're going to choose our 5 numbers from 1 to 59. That's going to be something different than choosing the Powerball number. We're going to do both of those things so we can multiply how many options there are for both. In all of these, we are going to be looking at without replacement, and order does not matter. This means we're going to be having combinations. So for the 5 numbers from 1 to 59, we are going to have 59 numbers total, and we are going to choose 5 of them. And for the Powerball number, which is from 1 to 39, we're going to have 39 options total. We're going to choose 1 of that number. So here this is going to be 59 factorial over 59 minus 5 factorial times 5 factorial times 39 factorial over 39 minus 1 factorial 1 factorial. We also need to think about our event. Our event E is we match all 6 numbers. And there's only one way to do this. So our probability is going to be 1 over whatever this whole thing is equal to. This is going to be equal to about 200 million. So our probability is 1, it's about 1 in 200 million. Not very good odds to win the Powerball lottery. All right, next we're going to talk about a game called Kino. Kino is basically like a lottery-like game played at a casino. You pick 8 numbers. In fact, there's actually different amounts you could pick for different games. Let's just say you pick 8 numbers out of 80 total numbers. You have a little scorecard here with your 80 numbers. And you choose 8 of them. If you match a certain number of the winning numbers chosen, then you get the appropriate payoff. So if you match, all 8 of your numbers are winning numbers, maybe they pick 20 of them or something, then you win a certain amount of money. Here we're going to say find the probability of having exactly 5 of your 8 numbers matching. So 5 out of the 8 numbers total are going to be matching. And I did forget to put here that in Kino, there are 20 winning numbers chosen. So first of all, S, the sample space, is going to be all possible choices of 8 numbers. E is going to be where we have 5 winning numbers and 3 losing numbers. So first of all, let's talk about the size of S. All the ways to choose 8 numbers is going to be a combination. The order doesn't matter. We're going to have without replacement, can't choose the same number twice. This is going to be 80 possible, choose 8. 80, choose 8. For E, we're going to break it up into 2 parts. We have our 5 winning numbers and we have our 3 losing numbers. We're going to multiply those together. So the ways to get 5 winning numbers, we're going to choose 5 things. And how many are we choosing from? We're choosing from the 20 winning numbers that we know are there. So it's going to be 20, choose 5. For the losing numbers, we're going to choose 3 of them. And we're going to choose from 60 losing numbers. 60 losing numbers, we're going to choose 3 of them. So our probability here is going to be 20 choose 5 times 60 choose 3 over 80 choose 8, which comes out to be about 1.8%. So 1.8% of the time you'll have exactly 5 numbers matching. Now to win, you can get more than 5 numbers matching and you get a bigger payoff. This is exactly 5 numbers matching. All right, let's talk about poker to end with. We don't need to know much about the game of poker, but what we're going to do is we have a 52 card playing deck, and we're going to be dealt 5 cards, and we're going to talk about different combinations of those 5 cards. So first, let's talk about the probability of being dealt 4 aces when you're playing 5 card poker. So let's talk about, first of all, the sample space is going to be all 5 card hands. And the size of that sample space is going to be 52 total cards. We're going to choose 5 of them. Note that the order does not matter here, because we can just change the order of our cards in our hand. Doesn't matter what order they're in. So 52 choose 5 is the size of our sample space. The set E is having 4 aces. So let's talk about that. We're going to have our 4 aces: ace of spades, ace of clubs, ace of diamonds, ace of hearts. So here are our aces. And then we have one other card. So how many ways can I choose the first 4 cards? There's only one way to have these 4 cards. You just have them. There's nothing else we can do. But there's a lot of choices for that other card, right? There are 48 cards left to choose from here. 48 is 52 minus the 4 cards, the 4 aces. So here we're going to have 1 times 48, 48 possible things. That's going to be the size of our event. 48 ways to get 4 aces in a hand. So our probability here is going to be the size of our samples, our event over the size of the sample space. 48 over 52 choose 5, which is going to be about 1 in 50,000. So note that another way to kind of think about these two numbers, 1 and 48, the 1 here, we could think about this as there are 4 aces to choose from, and we're going to choose 4 of them. 4 choose 4, but that's just going to be 1. And the 48 could be out of 48 total cards, we're going to choose 1 of them, but that's just 48. So we could think about those as combinations if you want, but it's almost easier not to. All right, next example. Find the probability of being dealt a 4 of a kind when playing 5-card poker. So again, our sample space is the same. 52 choose 5. But our event now is get a 4 of a kind. That is match 4 of the cards. So we have our 4 of a kind. They're all the same cards. And we have our 1 other card. So here, there's not just one way to get a 4 of a kind. In fact, there are 13 ways to get a 4 of a kind. That is, what number are you looking at? And we are basically just choosing one kind of card from 13 kinds. That is 13, choose one, which is 13. Is it the 4 of kind of aces, 2s, 3s, 4s, all the way to jacks, queens, and kings? There's 13 different kinds. Just like the other one, the other card, there are 48 other cards, and we're going to choose one of them. So total, we're going to have the size of E is going to be 13 times 48. And our probability here is going to be 13 times 48 over 52 choose 5. It's going to be about 1 in 5,000 if you do those calculations out. All right, and it's going to be exactly 13 times more likely than getting the ace of a kind, ace 4 of a kind, but we were kind of rounding the numbers because they're large numbers we're dealing with. Another way to think about this is we could do the probability of E here is the probability of getting 1s in a 4 of a kind plus the probability of getting 2s plus the probability of getting 3s. 1s are aces, I should say, all the way to queens and kings. And we found that each of these are going to have a probability of 48 over 52 choose 5. We're going to do that 13 times. It's another way to sort of think about breaking that up. And last problem here, find the probability of being dealt 5 hearts in 5-card poker. So once again, our sample space is the same. It is 52 choose 5. That's the number of ways that we can have 5 cards. But our event now is get 5 hearts. So note that there are 13 hearts in the deck, and we need 5 of them. So here, the size of E is going to be 13 total choices, and we're going to choose 5. It's 13 factorial over 8 factorial, 5 factorial, which is about, or exactly 1,287. And that's all of our options. So here, our probability is going to be 1,287 over 52 choose 5, which comes out to be about 1 in 2,000. So in all these problems, it takes maybe a little bit getting used to games of chance. Once we have that, it's actually fairly easy to understand the question, but the actual getting to the answer can be quite difficult. And we need to think about all of our counting strategies and don't be afraid to lay out what you're trying to do in front of you. Make a little diagram. Think about what you're doing critically, as that can be how we get to the right answer.